Okay, great. Let's go ahead and get started. Thank you, everybody, for joining us this morning or this afternoon, this evening, depending where you are in the world. My name is Matt Sanders. I'm the Program Director for the Pacific Ocean Energy Trust, and we're very pleased to bring you this webinar today, focusing on wind resource characterization off the coast of California. I'm just going to hit on a couple points administratively here. For best results, please make sure that your video is turned off and that you're muted. You shouldn't really have that capability within this webinar platform, but just in case you do, please make sure to stay muted throughout the webinar. Please submit questions. There's a couple options for questions. You can either use the Q&A function that you may see on your Zoom screen. You can also just please submit your comments in the comments section. It does mention here to submit them to Jason Bush, but if you could please just try to submit them to the whole group, that would be best. We'll do Q&A at the end of the presentations, so please just be patient. We'll address your questions at the end of the presentation, unless it's a short answer that a panelist sees and is able to jump on really quickly. And finally, this webinar is being recorded, and once we are able to process it, we'll be sending out a link and posting it on POET's website for everyone to see and share and review if necessary. So if we can go to the next slide, please. Just a quick run through of the different presentations that we'll be seeing today. Happy to discuss the introduction, start with an introduction to offshore wind resource characterization, move to state-of-the-art wind resource modeling for offshore California, move on to wave modeling to support offshore wind assessments, then enhancing the wind resource characterization through buoy-based observations, and then we'll finish with how wind data fits into offshore wind planning. Next slide, please. Those presentations will be given by the panelists that you see on the screen there. Just quick bios for each of them. Raghu Krishnamurthy is an earth scientist in the Atmospheric and Global Change Division of PNNL. His area of specialization is in atmospheric fluid dynamics, aircraft safety, boundary layer meteorology, remote sensing, sustainability engineering, urban air pollution, wind energy, and wind engineering. Mike Optis is a senior atmospheric scientist at NREL, the focus on mesoscale modeling, offshore wind resource characterization, and wind farm performance assessments. Advancing machine learning and uncertainty quantification techniques in these areas is a key research focus for Mike. Prior to joining NREL, Mike was a senior scientist at UL Renewables. Gabriel García Medina is a research scientist in PNL's Coastal Science Division. His main area of expertise is the dynamics of the coastal ocean. He works in projects in the areas of wave energy, tidal energy, and coastal flooding. Alicia Gorton is a project manager and ocean engineer in PNL's Coastal Science Division. Alicia serves as the program manager of the LIDAR buoy program and also contributes both her technical and management expertise to several projects related to environmental effects of offshore wind. Lastly, Frank Pendleton is a GIS analyst for the Bureau of Ocean Energy Management, Pacific Regional Office. He works with various subject matter experts to analyze data for offshore wind planning efforts. So we're really looking forward to everyone's presentation. At this point, I'm going to hand it over to Raghu to go ahead and get started.
All right. Okay. Thanks everyone for joining, and thanks for the lovely introduction. So I'll go ahead. So today I'm just going to be I'll be talking about a brief introduction to offshore wind resource characterization. I won't be doing justice by giving a 10-minute talk and trying to explain everything about wind resource characterization, especially offshore. So I'll be hoping to get a lot of questions from you on various aspects of it. But what we'll primarily be talking today is generally what we mean by offshore wind resource characterization. What are the various metocean parameters we plan to collect during a wind resource characterization campaign? What sorts of instrumentation is generally used? And a little bit more about the offshore modeling. So in general, it's good to get the definitions out of the way. And one of the definitions of wind resource characterization, it basically involves collecting information about various metocean parameters that affect the wind resource of a given region of interest and which would also help in the wind farm performance and forecasting or predictability of a particular given region of interest. And you can see a map here by NREL, which basically shows the wind resource for the eastern, for most of the seaboard across US, and there are pockets of extremely high wind energy potential, for example, on the northeast coast and close to California, above the California Bight. So you can see some really nice locations where there is a lot of potential for putting up floating turbines or putting up a lot of different kinds of turbines. So the various stages of an offshore wind project or any wind energy project, you basically start off with a pre-development stage, which lasts for a year or two. Then you have a development stage, which basically entails the entire wind resource characterization stages. So these two are primary stages where we collect information for a given region of interest and try to analyze the potential of that particular given region for wind energy. And then from there on, you have construction and commissioning, and then operation for 20 odd years, and then finally decommissioning or repowering, depending on the project. So now what's different offshore? We know that we've put in several turbines on land. There's one key difference here is that we have this ocean, right? So the whole ocean interacts and influences the atmosphere. So this was a very nice illustration in one of the papers in the citation below, which encapsulates a lot of the different processes which occur in an offshore environment. For example, there's the land and sea breeze events, which kind of influences and can also interact and produce internal boundary layers. There's the fronts, especially in the Gulf streams, which basically influences the wave and the wind characteristics around that region. And then there's lag mode circulations, which influences the coastal upwelling and the economic transport. So there's a lot of processes which influence each other. So one of the large scale, or a few of the large scale processes are El Nino, which influences the entire globe, but also areas around the US. And then especially in the US, there's a north building current, which kind of influences a little bit about the sea surface temperature difference and kind of changes the stability across the different region. From large scale, if you want to go slightly on a smaller scale or mesoscale processes, then you have the coastal upwelling, which basically pumps in a lot of the fresh water or cooler water from underneath onto the surface, and it kind of creates a much more stable environment across the atmosphere. And then you have land and sea breeze events during daytime and nighttime, which again has a different impact, especially for wind energy. And then once you have extremely stable conditions, you can also see low-level jets. In some cases, for example, in California, you'll see really low-level jets, which really influence the wind energy, and that has to be taken seriously in accounting for loads for a particular given wind turbine. And then once you start going into much more smaller scales, you have the air-sea exchange processes or air-sea interaction effects, which basically are the momentum transfer, the heat transfer, and the humidity transfer because of the huge ocean, which influences the atmosphere. And then you have these small sea sprays because of wave breaking, and that also increases the latent heat around the region and kind of influences a lot of the stability across the domain. So all of these processes are not individual. They don't happen individually, and you can quantify them individually. So there was a beautiful paper by Edson, which kind of makes or encapsulates all these processes and connects them or links them up. And you can see this complex process which the atmosphere kind of interacts. And again, this is not everything, right? So there's a lot more which is broadly brushed out in this particular slide, but it kind of gives you an idea of the various processes that govern the transfer of heat, mass, and momentum within this boundary layer, which is basically a coupled boundary layer. So some of the notable US offshore phenomenon, because we're talking about having wind turbines in the US right now, especially offshore. In the East Coast, we see a lot of these sea breeze events, low-level jets, and also Gulf Stream effects across the East Coast. And this is quite well known. Whereas in the West Coast, some of the effects which are known but not quite well known, and how they influence the offshore conditions. You have an extremely very shallow or stable boundary layers, which was identified quite a while back, primarily because of, again, coastal upwelling. And then you have harsh wave conditions, again, because of the depth of the western bathymetry. And then you have topographically induced winds, mainly because of these Santa Ana winds, which give you a lot of the winds offshore and can create extremely high wind conditions during certain cases. And also you have the California Bight, which kind of creates circulations or eddies around that particular region, which can be dangerous for wind turbine operation. And some of the other more extreme events, which are known or which are pretty much well known, occurs in the East Coast, the hurricanes and the nor'easters, which can be devastating for wind turbines if not properly planned. And here is one example on the Gulf of Maine, which basically shows the low level jet, where they had a ship and they were transecting across various locations, and they saw the evolution of the low level jet at a given particular location. And you can see that's right there the sweet spot of a modern generation offshore wind turbine. And you can only imagine the impacts of such a low level jet on wind turbine loads.
Raghu, this is Jason. Unfortunately, there's been some problems with the audio quality. So
okay.
A lot of comments that it's hard to hear you. And indeed, on my end, it's going in and out a little bit. So I guess there's not much we can do on the technical side, but perhaps speak into the microphone a little bit more and maybe slow down just a little bit, and it'll fix as best we can on the fly here.
I see. Okay. How is it now? Is it better right now?
I think it's just the bandwidth issue. It seems like everyone's having the same sort of garbled digitization sound. So I think just slowing down just a little bit will be about the best we can do at this point.
Sounds good. Okay. Okay. Sorry about that. So before we, so the next thing that I wanted to talk about was what exactly is a marine atmospheric boundary layer. So imagine my squiggly line here is the other waves of the ocean, and you have your wind turbine rotor layer approximately about 80 to 200 meters. Right. The bottommost 1 meter deep atmospheric marine boundary layer is basically a lot influenced by the waves. Right? So you have wave influence on the winds and the winds influence on the waves, and you cannot ignore the coupling over there. Then you have the surface layer, which is slightly above and up to about 50 and 80 meters above the sea surface layer, where you can do a lot of your you can use a lot of one in the book of similarity theories, which basically assumes that the winds are horizontally homogeneous, they're stationary, and the fluxes within that surface layer are constant, are near constant. And you can use these similarity relationships to extrapolate winds within the surface layer. And this is generally on the order of about 10% of the depth of the marine boundary, right? So, and then you have the entire boundary layer, or the marine boundary layer, where the friction effects of the offshore of the ocean is still felt, and it depends on what kind of turbulence mixing you have, either convective or stable conditions, and we'll talk a little bit about that. And this is generally on the order of hundreds of meters from the surface layer. And above the marine boundary layer height, you have the free troposphere, where it's no longer impacted by friction of the ocean, and it's generally decoupled in that sense. So this is the effect of the wave surface on the marine boundary layer. The next one is basically going to be talking more on the lines of the effect of the marine boundary layer with regards to stability. And you can see here we plotted on the left side you have the convective marine boundary layer, and then on the right side you have the stable marine boundary layer. And what happens in a convective boundary layer, it basically enhances turbulence production, and this intensifies the exchange and the momentum distribution within the marine boundary layer. And you can see that the potential temperature is generally near constant within the marine boundary layer in a convective case. Whereas once we come into a stable boundary layer, you basically, the turbulence produced by shear is suppressed. And this creates a weak exchange or a weak coupling with the surface. And you can see that the potential temperature kind of increases as you go with the function of height. Now, the key thing here is that if you look at the marine boundary layer height, which basically tells you a little bit about the decoupling of the surface, you can see that during stable conditions, it's very, very close to the surface or to the sea surface, whereas in the convective conditions, it's pretty high up. So this can cause the models to go crazy with how it can actually predict most of the winds. And also, most of the theories, what we have, do not really fit well in stable boundary layer conditions. So there's a lot of issue here, especially in stable marine boundary layer conditions, where the models go wrong, where we cannot really do a good job in predicting, and it can also cause a lot of low-level jets, which affect the wind turbines. So, what do we have to measure? So there's a lot of meta-ocean parameters we can measure, but some of the key parameters what you would measure in an offshore wind resource characterization campaign would primarily be a wind speed profile from surface up to the marine boundary layer height, ideally. Generally, right now, they only measure it up to about 200 to 50 meters above sea surface layer level, which basically encapsulates the rotor layer. Then you have the wind direction profile from surface to the marine boundary layer height, temperature and relative humidity profile. These are key for understanding the stability of a particular given atmosphere. The surface wave characteristics, which Gabriel is going to talk about a little bit more on significant wave height and how they influence the atmosphere. The ocean currents underneath, which tells us a lot about the upwelling information and salinity information on the freshwater intake, and that is important for understanding how they interact. The sea surface temperature, especially in the Gulf, tells us a lot about in which direction the winds are going to go, the atmospheric pressure, and especially on the West Coast, cloud properties, for example, the base height, thickness, and the water path and phase are extremely important because you see a lot of fog and low-level clouds offshore. So West Coast cloud properties are going to be more and more critical. Now, one thing is that these observations also need to span all seasons. They need to be made across regions with gradient mean wind in order to make sure that you're accurately capturing all of those processes. And also they have to be made at different water depths, because as you can imagine, the effect of the coastal bathymetry would influence the atmosphere quite a bit. Now the instrumentations. So there's been a lot of research done in the research side of things, not on the industry side of things, but on the research side of things for decades. And one of the primary instrumentations what people most often rely on are basically in situ sensors, which basically is at a given point in space. And one of the ways to do that on land is they basically put up a tower, and offshore you have a similar kind of a setting. This, of course, is extremely expensive. You have to, depending on the water depth, it can go up to tens of millions of dollars to just put up an in situ mast. Then the other offshore instrumentation platform is the buoy, offshore buoy, which basically gives you a surface measurement, ocean and currents, and remote sensing. These are an order of magnitude lower than the in situ sensors and gives you a lot more information, which comes in handy. Another interesting piece is the X-band radar, or the coastal radars, which are situated on land and can measure sometimes about 30 to 40 kilometers offshore. And this technology is just advancing in time, and we may see something which can go up to 60 kilometers or more than that in giving very, very high resolution measurements. And some of these go further away, but giving X-band bandwidth, that technology is a key in understanding a lot of the offshore processes. And other interesting instrumentations, which mostly used in research, but are drones and gliders. Drones are basically used primarily for understanding sea surface temperature, but also for wind measurements across a given line. And the gliders are mostly automated. In that sense, they can actually go across various locations, uninhibited, and they can provide you sea surface temperature, salinity, various other parameters which are important for understanding how the ocean interacts with the atmosphere. Another one is your satellite remote sensing, and we'll touch a little bit about that. As you have the synthetic aperture radar, which provides you across the globe measurements. Of course, the information what you get from a satellite is much more on a shorter time scale compared to from one of the other measurements. And another interesting part, what research generally focuses is using research vessels, where they can pack in a lot of these instrumentations and take the ship across the various locations. And this way, they can actually get a lot of the information what would not be available from these other sensors at a given point or location. So what do we have right now? So there is an existing instrumentation network, especially East Coast. You have this New York Mesonet network, which spans across the entire land. And then offshore, you have the NDBC buoy network. You can see the locations over here. They basically span most of the US coast and they give you a lot of information, valuable information. And you have the satellite measurements, which can provide you sea surface or surface winds all the way from 1985 to 2019. And you can see that it's about 30 years of information of sea surface winds can be obtained. Now, what's lacking is we lack hub height measurements, which is kind of critical for a lot of these model validations and improving our understanding of offshore wind resources. So what exactly do these models do, right? So you have different kinds of models. So one of the models is basically a microscale model, which generally are on order of about 10 meters or lesser. And they involve computational fluid dynamics or large area simulations, which can give you high granularity of information of how, for example, in this case, what we're showing is an LES model for a wind farm in Europe, and they can really see how the wakes are interacting with each other. And this kind of information is really critical, which tells you a lot about how the winds are behaving, or the wakes are interacting in this case. And the other models, which are on the order of about a kilometer or so, are the WRF models, or the weather research forecasting models. Here it's on the order of a kilometer, so you can actually span across the entire US, and you can see a lot of the maps which are generated by Pendleton or by AWS TruePower are basically using something of a similar kind of mesoscale model to generate these maps. They're slightly coarser than the microscale model, but they provide you good information that can be used for your initial pre-developmental stage and later on in the post as well. But more so since we're talking about a coupled environment, I spoke so much about SC interaction. The future in this domain is basically a coupled model. And one of the ways to do it, I'm not saying the only way, but one of the ways to do it is as a COAST model, which is a coupled ocean and atmosphere wave sediment transport model by USGS, initially recommended by the USGS. And this takes into account the various features, the processes, what we spoke about earlier on, and how that interacts with the atmosphere. So these are the various offshore models, atmospheric models, which are being used in the offshore wind resource characterization processes right now. So what's the future? So the future right now is that we can see that although US is lagging a little bit behind, the global wind industry installed about 5,000 plus megawatts of offshore wind capacity in 2018. So there's a lot of catch up to do. And California is definitely a sweet spot. And you can see the BOEM locations where people are, where the leased areas are currently in the Diablo Canyon, Morro Bay, and Humboldt. And these are primed right now for development. So what do we foresee is there's an accelerated growth in the next decade, where it's going to increase, or it's going to change from about 154 gigawatts to 193 gigawatts by 2030, and much more longer range predictions by 2050 is going to be about 500 gigawatts of offshore wind energy, which is really interesting. And in the sense of, and especially in places like California, where you have the very deep bathymetry, floating offshore wind pilot projects are advancing quite a bit. The global pipeline is generally about 3,100 megawatts. There are about 29 different projects announced with 44 megawatts of operating projects. So there's a lot more in stock for offshore wind resource characterization, and trying to understand this is just the beginning of how US is going to change its energy portfolio in the coming years. So, and these are some of the references what I've used for future study. So, thank you. Mike, you must be the host.
Yeah, thanks, Raghu. Am I coming in okay?
Yep.
Yes.
All right. Thanks everyone for joining. I just want to make sure, are you looking at a presentation?
Yes, we see your screen.
Right now? Perfect. So I'm Mike Optis, an atmospheric scientist here at NREL, and I wanted to present today on a new data set, a new offshore wind data set we produced for offshore California. Also acknowledging Alex below, Ph.D. candidate at CU Boulder, who helped a ton with this work. So I guess before starting discussing the new data set we created, I think it's worth discussing the one we're replacing effectively for offshore California. So a lot of you might be familiar with NREL's Wind Toolkit that was produced back in 2013. As Raghu mentioned, in mesoscale modeling, a lot of this is done using the weather research and forecasting model. And this was the same model that was used back then using version 3.4 at the time. Just a couple of details on the data set. It is a 7-year time series data set being provided at 5-minute time resolution and 2-kilometer spatial resolution. And so even now, 7 years later, I think it remains the best available public data set for wind resource assessment across the continental United States. The data is pretty easily accessible through both web and API interfaces, providing wind resource data every 20 meters up to 200 meters above ground or sea. So it's been a great data set, used a ton for a range of wind energy applications over the last 7 years. So the question is, why are we now moving to replace it, starting with offshore California? And the short answer is that 7 years is quite a long time when we're talking about research and development in the numerical weather prediction modeling space. For example, we're now at WRF version 4.2 compared to 3.4 from the Wind Toolkit. And that's more than really just a number. There have been extensive improvements in the WRF model over the last 7 years. A lot of this has been driven by dedicated field campaigns to improve WRF performance, particularly for wind energy applications. So accurately modeling the winds, say in the lower 200 meters. One example of this would be the Wind Forecasting Improvement Project number 2, which was a very extensive field campaign funded by the Department of Energy in the Pacific Northwest, aimed at improving WRF in complex terrain. And more than just WRF improvements itself, over the last 70 years, we've seen state-of-the-art input data products that are used to provide boundary conditions for the mesoscale simulations. So this would include novel products like the ERA5 reanalysis, as well as new land use and terrain data and sea surface temperature data. Another reason to update the model is the 7-year time period for Wind Toolkit, going from 2007 to 2013, is generally insufficient for long-term analyses of the resource or energy production. So just as an example, on the right, I'm showing annual average wind speeds at modeled wind speeds at a buoy location off the coast of California. And the Wind Toolkit period is shown here in between the dotted lines. And you can see that if you just looked at the Wind Toolkit modeling period, this looks like an extremely stable resource year to year. When you in fact extend it out to 20 years, the true variability of the resource comes out. So having a longer data set captures the true variability in that sense. Finally, the Wind Toolkit was pretty minimally validated offshore, just using a couple surface buoys. And that said, we don't have a great idea of how well WRF is performing there. In the last 5 years, as Raghu mentioned too, the deployment of floating LiDAR is really starting to change that, and it's offering pretty novel opportunities for offshore wind validation. So those are most of the reasons why we redid the data set. Probably the most exciting for me at least is the need to quantify our confidence in modeled wind speeds. These are based on their modeled results. They're not perfect. They're going to deviate from observations. And about a decade of research has pretty well demonstrated that modeled wind speeds in WRF can be quite sensitive to the inputs and setup within the model. And so for illustration, I'm plotting just a sample 4-day period of 100-meter wind speeds off the coast of California. I think I forget what point it was. And just running it through a 15 megawatt IEC power curve to get a sense of the power given these wind speeds. So you can see a nice ramp event here where the power reaches peak capacity for this model setup. If we run WRF with a slightly different model setup, but totally reasonable, you can see the deviations between the two setups. And in some cases, we even get a peak wind speed here, which actually triggers the cutoff wind speed, and we actually get 0 power, so a lot of sensitivity in the power. And if we keep going and we start running a lot of model setups or ensemble of setups, a picture like this starts to emerge where we actually see and get a clear picture of what the actual variability in the WRF model might be. If we can distill that then into some confidence metric, in this case, the standard deviation, we can then disseminate this information, our best estimate of the wind resource in blue, along with some metric of our confidence based on the sensitivity of WRF itself. So the idea that numerical weather prediction models are sensitive isn't anything new, but we're trying to at least push the state of the art by starting to disseminate this information in wind resource products, starting with the offshore California data set. And what I mean by disseminating, we can apply this approach across different timescales and start to produce maps or time series data and disseminate the result. So jumping ahead a bit, this is showing our result of the model sensitivity or confidence or uncertainty in the annual average wind speeds off the coast of California. So blue is low sensitivity, yellow is high, ranging from about 1 to 7%. And what we see is that depending on the model setup, we tend to see a lot more sensitivity close to the coast, and there's good reasons between the land and sea interaction, for example. And within these call areas, as shown here in red, we get quite a bit of sensitivity, so almost 6–7%. So that is kind of our interpretation of our confidence of the data we are starting to disseminate. So a lot of background on why we're trying to push the next generation of wind resource data sets. Let's start with what we've actually done so far. So our new 20-year offshore wind resource data sets are going to feature a 20-year time period based on 16 different setups to the WRF model, where we consider variations in parameters that are known to drive changes in the wind speed. So that includes the large-scale atmospheric forcing we're using, the sea surface temperature forcing, critically the planetary boundary layer scheme. So Raghu touched on this, how winds are modeled in the lower 200, 500 meters of the atmosphere. Within WRF is really critical in determining what the wind profiles look like. And there's a lot of different ways that this can be done in WRF. So it's quite a sensitive parameter. And finally, the land surface model, how the land interacts with the air and exchanges, heat and moisture, for example, ends up being pretty important in coastal offshore wind modeling when we consider roles of the sea breeze, for example. So in addition to these ensemble runs, we are going to be disseminating sensitivity metrics for the 100-meter wind speeds at 5-minute time resolution. So our pilot project was this offshore California data set. We completed it this year using funding from the Bureau of Ocean Energy Management, Pacific region. So we were super excited to be able to take these ideas that we've been wanting to do for a couple of years and partner with BOEM to actually implement this. So this is an example of a map that you're all pretty used to seeing, I'm sure, showing the mean annual wind resource with the new data set. And I'll start comparing that to the wind toolkit in just another slide. But first, I wanted to talk about how to find this data. It is now publicly available for download. If you're looking just for a single site, the easiest thing to do would be you go would be to go to the wind prospector tool that we have listed here, where you can see, you can pick your year, pick the data that you want, even the time interval, and be able to download this data pretty quickly for a single site. If you're looking for a lot of data or regional data, we really recommend finding someone with some pretty basic Python skills and leveraging our Python-based API code base listed here on GitHub, which an example snapshot of what you can type in to pretty quickly get a lot of regional data from these new runs. And like the wind toolkit, we're providing data every 20 meters up to 200 meters, including wind speed and direction, temperature, pressure, relevant surface variables, and also relevant turbulence and stratification variables. So that's the whole new data set. I think there's a lot of interest in how this compares to the wind toolkit, and this ends up being a pretty important comparison. I'll show on the next slide. So here we're comparing our new data set with the old data set in terms of the 100-meter mean annual wind speed. So on the left is the new, center is the wind toolkit, and if we subtract one from the other, we get the difference. And in this case, red means that we are modeling higher wind speeds with the new resource data set. And as you can see, it's pretty red across the board, especially in some of these coastal areas where we're seeing increases in the mean annual wind resource up to 1.5 meters per second. Pulling out information from the 3 call areas, we see a range of 1 to 1.5 meter per second increase and 10 to 20% percentage based. So we recognize that this is a substantial increase in the modeled resource. We've done a ton of work to understand and explain this increase, and we believe that this new data set is more accurate. And I'll just touch on some of that explanation in the next couple slides. It turns out a lot comes down to atmospheric stability. And as Raghu was mentioning, the role of atmospheric stability in driving high wind shear or low level jets tends to be really important actually in offshore California. Specifically, what we're doing here is we're calculating a stability metric, the bulk Richardson number specifically, between a surface and 200 meters. And we're plotting maps of the frequency of occurrence for each stability regime. So dark is not frequent, yellow is very frequent. And again, these lease areas in red. So what we're seeing in offshore California from this new data set is it doesn't spend a lot of time in unstable conditions, again, and I was alluded to in the last talk, it spends a ton of time, especially close to the coast, in very stable stratification, at least half the time for these lease areas, and even 70% very close to the coast. And there's good reasons for this. We know that cold water through coastal upwelling comes up to the coast, close to the surface, and when that interacts with warmer air above it, you're essentially inducing a stable stratification, which leads to very interesting wind resource characteristics. So how WRF models that ends up being critical in explaining how we have this difference between the wind toolkit and the new data set. I'm specifically looking at these planetary boundary layer or PBL schemes in WRF and how they account for wind profiles. So I'm going to gloss over a ton here just because we don't have a lot of time. But essentially the old wind toolkit used a PBL scheme from Yonsei University, which was pretty popular and well used at the time. Whereas the new data set is using this Meller-Yamada, Nakanishi, Nino, or MYNN PBL scheme. I don't have time to explain the differences between the two, but they are significant. And critically, both schemes, they're known to diverge in stable conditions and perform pretty differently. That said, there's been a lot of research into MYNN over the last 5 years. It's been the focus of a lot of improvement in WRF, and it's really become the state of the art for wind resource assessment and is known to be more accurate in stable conditions. So that's, for these reasons, we went with this scheme as well. And if we actually compare the two, which we did a lot of sensitivity analysis for offshore California, you start to see the impact of a PBL scheme in WRF. So here, recall we have 16 ensembles in this modeling that we're doing. They're all shown here, color-coded based on which turbulence scheme they used, YSU or MYNN. And here we're looking at the annual average mean close the Humboldt call area. And pretty critically, you can see that the 16 ensembles definitely separate into 2 distinct groups depending on the PBL scheme used, with MYNN having significantly higher shear and about 1 meter per second higher wind resource on average at 100 meters. Like, we're used to seeing this performance in stable conditions in other areas, but I don't think we've ever seen such difference on the annual average mean as we're seeing in offshore California. And I think that speaks to, again, how very stable the conditions actually are out there. So a natural question is, do we validate and confirm that MYNN was performing better? And the answer is yes, but we need better validation. At present, there's no offshore floating LiDAR publicly available for California. But if you wait for Alicia's talk, you'll hear about what's happening on that front, which is super exciting. So instead for this work, we did a lot of validation at buoy-based measurements below 5 meters and leveraging some coastal onshore radar where we could. We found that MYNN did perform better. It was kind of marginal at these lower heights and on land, and wasn't able to fully explain this big difference in bias that we're seeing. So we really need to do more work, and we're very excited to validate once this offshore LiDAR in California comes available. Very quickly, future work, we want to cover all offshore areas. So with BOEM Pacific funding, we've done the California resource data set that's available. And over the next year or a year and a half, 2 years, we'll be filling out every offshore region using an award from the National Offshore Wind R&D Consortium. Finally, we've talked a lot about the uncertainty in the resource and how it's important to quantify that. And the key question is, how does this sensitivity in the modeled wind actually translate into these analyses that we really care about? CapEx, net capacity factor, levelized cost of energy. And that's really going to be the big impact. How do different WRF setups propagate and create different results? And we'll be exploring that a lot through that award in the next year. So, thank you. And Alicia, can you remind me who I'm turning the screen over to?
Gabriel.
Thank you.
Yep.
Okay, you should have control now, Gabriel.
Yes, I got it, thanks. Presentation together. Right, can someone confirm you can see my screen?
We can see it.
Okay, awesome, thank you. So I was asked to talk a little bit about wave modeling and some wave climates and how this can be used to support offshore wind assessments. Next. So I'm gonna refer to waves a lot, but just so we're on the same page, we're gonna be talking just surface gravity waves. And what we're looking at is the generation of waves, propagation, all the way to shore. So this little cartoon from Paul Comer showing the different stages that when we model waves, we need to make sure we're considering. When we talk about the wave climate, it's very different in the East Coast and the West Coast. And the reasons for that are, well, just how different the ocean is and the sources of waves that can get to a single point. So here I am showing, to give you an example, the sources of energy that approach a point offshore Oregon in the left side and offshore of the Carolinas in the right side. In the contours is the days that take those waves generated at that point to reach the point of interest. And then in the colors, what you can see is how what kind of energy can arrive to that point. So when you're looking at the West Coast, the energy that's generated from the Southern Ocean takes about 19, 20 days to get there, but it gets to offshore Oregon and California. And there's also a lot of wave activity from the North Pacific that arrives to that point. In contrast, in the East Coast, you have shorter periods. So waves that have been generated about 6 days before and also lots of local wind generation. So the way your waves are looking like will be kind of different. So we can see that here in this cartoon where I'm going to show the wave climate in the North Pacific and then in the East Coast. So looking in the left-hand side, you have 3 arrows showing those directions where that energy is coming from, and it kind of relates to the figure that we show below. And here on the right, you have a lot of generation coming kind of from the south, impacting the Northeast. So it has a strong seasonal signal. The table here in the center shows the averaged joint probabilities between your month and the periods of the waves. So for the West Coast, you have longer period waves. You're looking at 13 to 15 seconds in the winter, and then very calm summers. While when you go to the East Coast, you have more of a uniform, so longer winter, shorter summers, but you do have your waves are shorter, and that's because of that generation fetch is much less. As Raghu mentioned, the extremes are different, so the drivers of the extreme events are different. You have nor'easter and hurricanes driving those extremes in the East Coast, and then extratropical storms in the Pacific, and these will have different signatures. So these extratropical storms will generate these very long swells as they travel through the North Pacific. On the right side, you have 2 figures. On the top is the mean trend of wave height derived from altimeters. And as Raghu mentioned, the altimeter coverage is been very, very long now, over 30 years. So you can start doing statistics. And the reason I want to include this here is to show you kind of if you come from the East Coast, what kind of environment you'll be setting into. So the mean trend in wave height is going down in the Pacific, interestingly, and then across the North Atlantic, there's an increase of about 50 centimeters, 5 centimeters, well, 5 millimeters, I'm sorry, per year. When you look at the extremes, though, you have that the extremes are growing in the Atlantic as well, but then offshore California, it's been found that the extreme events are increasing at a high rate as well. So in terms of modeling these waves, the models themselves are different from WRF or ocean models that you might be used to because of the scales of the waves. So here I drew a cartoon based on wave theory, where we have a 3-second wave, so fairly short active generation zone at, let's say, 14 meters, because I just picked that. So to discretize that wave, you really need a resolution very fine, looking at like a 3-meter resolution to only get 5 points. So what we do is work on frequency domain and talk about the energetics of the sea state instead of the single wave. So here's an example of how it looks like. It's a very famous experiment offshore Denmark when the wind was blowing offshore, and there were wave staffs in these 5 locations. When you compute the spectrum here, you were able to kind of reproduce in frequency space how the sea state was evolving, and that's kind of the idea behind all the major wave models. And I'm putting here the kind of the governing equation for these models, where, see, in the left-hand side, all you have is you are advecting, so moving that spectrum in time if waves in space, and if waves turn because of bathymetry, you also consider that. And then on the right side, you then parameterize all of the physics, like winds, when waves break, bottom friction. And this is kind of the backbones of the major models like WaveWatch and so on. So these models are very capable, and I'll show you some examples why. Here on the left-hand side is some work we've been doing in the West Coast, and you have wave spectrum measured on the left and modeled on the right. In the colors, so the hotter colors will indicate more energy. As you move in the radial direction, means the waves become shorter as you go outside the circle, and directions are in nautical convention. So these models are able to reproduce quite well some local wind generation, and then waves, and then swells coming from the south. So which again kind of maps from that first figure of the generation areas I was showing. The waves have a very strong seasonal signal. So here are some wave roses offshore of the West Coast, and for the winter here and the summer on the right. In the winter, you have more directions offshore of California. But South California is more clean, everything mostly coming from the west. Now, in the summer, then that kind of flips. So Northern California has a more uniform direction because of the wind, because of the northerly winds. And then in the south, you have some swell coming from the south and then local generation. Now, these are normalized. So if you look at the very right figure, you see that the winter is much more energetic than the summer, and it has a longshore pattern. So as you get north of the Point Concepcion, you'll see how it becomes exposed to these very big storms, and the energetics are about 20 times larger. And what I'm showing here is wave energy. So wave power, so that's related to significant wave height squared times the wave period. So kind of includes those two parameters. Now, these models we are putting together at PNNL and NREL are high resolution models focused on the coast. And you might ask yourself why, and the reason is you can have very significant difference in wave climate when you are points that are 10 kilometers apart. And here's an example that I just picked, where offshore of California, where you have a hotspot where a lot of waves concentrate here in red, and then in the cooler colors, you have the opposite. And now when you look at the directions, you have waves coming from many directions in the north point, and then in the south, the canyon kind of filters things out, and you have a dominant westerly direction. So those might be things to consider if you're looking in a smaller area. There can be big differences in your waves. So Mike also mentioned how important longer records are, and it's also true for waves. So what I'm showing here is the anomaly in wave power again from a 32-year simulation at different points along the coast. 3 of them in California, and then 1 in Washington. You can see anomalies in the wave power that exceed 10 kilowatts per meter. And they match quite well with the El Nino index. So we have 2 big El Ninos in the early 80s and 97, 98, and a longer El Nino index. This was a 2-year El Nino, also generating large anomalies. So as we perform these new assessments, we want to make sure that we cover longer periods so that you can make your risk analysis with more confidence. So NOAA has done an excellent job of having a hindcast that's over 40 years long. They have global coverage and time coverage and shelf scale coverage as well. And then what we're doing at the Department of Energy and the national labs is complementing that in the last few kilometers near shore. So we are in the process of making those data available. NREL is the lead lab on making it available. So just keep your eyes open for it, because I think it'll be a good product for your studies. So Raghu kind of alluded to, so what's next, and we're looking at the full system now, and how instead of looking at just waves or just currents or just the wind, and this is where these kind of buoys, like Alicia is going to talk about, are becoming very important, because they can measure waves, currents, and wind. So here I'm showing you an example, kind of cherry-picked from a storm in January 2016, and how looking at the full system really helped us characterize the climate there. So on the bottom right corner are the observations in orange of wave height, and the system that includes waves, currents, and the wind makes very good predictions of the peaks of the storm. But when you don't consider things together, even if you do some calibration, it becomes very difficult to pick some of this. And this is where things are moving also from the oceanography side, and we're taking advantage of the improvements that have been made from the offshore wind efforts. Let's get this one. So what does it mean for the wind? So let me, the bottom left corner, you have bottom stress from WRF for 4 different scenarios. And this is a study from John Warner at USGS. And if you, depending on the combination of models that you use, or things you consider, your bottom stress can look very different. Where a standalone WRF can predict strong bottom stresses around the hurricane, when you consider the full system, because the currents and the waves, that will certainly look different. And so in terms of what does it mean for the wind per se, if that's a parameter of interest, that's still an area of active research. And here's an example of the percent difference in the 10-meter wind speed if you consider waves and do not consider waves. So the Taylor element considers their surface roughness based on waves. And since waves are a non-local property, it looks quite different from your core algorithm, which estimates your bottom roughness based on the local winds. So that might, under certain scenarios, give you differences of over 10% in your 10-meter winds. Yeah, I guess that's all my slides. If you have any questions, things that I glossed over, just feel free to put in the comments.
All right. One second here. Can everyone see my screen?
Yeah, we got you, Alicia.
Excellent, thank you. All right, so hi everyone, my name is Alicia Gorton. I'm with Pacific Northwest National Laboratory. As they mentioned in the beginning, I'm the program manager of the DOE LiDAR buoy program, and so today I'm going to build on what Raghu, Mike, and Gabriel talked about and talk about kind of how we collect all of that data to enhance wind resource characterization through buoy-based observations. And so just an overview of what I'm going to talk about. I'll talk about some motivating factors and drivers for this work. I'll give an overview of the DOE buoy program. I'll talk about some previous, recently completed, and near-term buoy activities, including the deployments off California, and then finish off with a summary. All right, so some motivating or driving factors behind the buoy program. So DOE held a workshop back in March of 2019 entitled The Research Needs for Offshore Wind Resource Characterization. And this really was driven to identify key knowledge gaps that can be effectively addressed by researchers with key current and emerging observational and modeling tools. This workshop brought together a bunch of folks from the wind industry, including industry, researchers, consultants, and government agencies. And some of the things they talked about here were topics related to industry requirements for offshore wind information, metocean information for loads engineering, the current state of offshore modeling and observation, and also the needs for metocean information improvements. There was a workshop report that was published that goes into all of the gory detail that they talked about at that workshop. And the key scientific challenges that came out of that workshop and are articulated in this workshop report are informing DOE and others in making decisions about potential R&D efforts for offshore wind. And they're also informing DOE in terms of their investments. And one of the investments that they are making is in the LiDAR buoy program. The LiDAR buoy program includes 2 Axis wind sentinel buoys that are deployed off the coast of the US to facilitate met-ocean data collection using validated methods to support the development of standards to collect information that's needed by the US offshore wind industry. And here's just a general overview of the timeline of the program. So 2 Axis wind sentinel buoys were procured in 2014. They underwent acceptance and performance testing at our Marine Sciences Laboratory in Sequim, Washington. They were transported to the East Coast and deployed off the coast of Virginia and New Jersey between 2014 and 2017. They underwent significant upgrades in 2019, including upgrades to their LiDAR systems and some data logging systems. They underwent an offshore validation campaign to validate the LiDAR systems in compliance with Carbon Trust standards in 2020. And now the buoys are staged in California to be deployed in the next couple of weeks in partnership with the Bureau of Ocean Energy Management. As part of the buoy program, there's a subsection of the program where we lend buoys to qualified parties to acquire wind resource characterization and oceanographic data as part of a buoy loan program. And as part of that program, the buoys can be borrowed for 12 months at a time to be deployed, and the loan partners assume full responsibility of the buoy. The buoys have to be returned to PNNL in fully functional condition, and DOE does not provide any funds to support the deployment through this loan program. We have a lot of program material on the overall buoy program and how to borrow a buoy on our LiDAR buoy website. So if you just Google PNNL or DOE LiDAR buoys, it'll pop right up and you'll see a lot of information in terms of a report that goes into all of the gory detail about the loan process. We have some brochures there as well. And data access is a critical component of the overall buoy program. And so all of the data that's collected on these buoys is made publicly available for free on the DOE Atmosphere to Electrons Data Archive and Portal. And so we have all the information and all the data there from the deployments off Virginia and New Jersey. We have data there from the validation campaign that finished in April. And as soon as the buoys are deployed off California, the MedOcean data from those deployments will be made available on the DAP as well. All right, so in terms of the instrumentation that these buoys are equipped with, we've kind of categorized them into 3 different categories. First, we have instrumentation related to power, data, communications, and navigation. So in terms of power, these buoys are mostly powered by renewable sources from a turbine and 2 solar panels. There is also a diesel generator in a compartment on each buoy. However, that is rarely used. In terms of data acquisition, we have data loggers. There's also an industrial personal computer that integrates all of the data streams together. Depending on where the deployments are, if they're near shore or farther offshore, you can communicate the data back to shore via either cellular communications or satellite. We show those antennas here. We have navigation lights for navigation safety, AIS, which is kind of an automatic tracking system for seagoing vessels, and then also a radar detector or a radar reflector. On the meteorological side, in terms of instrumentation, we've talked a lot about wind profiles and LIDARs. And so the instrumentation here, that's labeled as number 11. That is our new LIDAR system that was validated just a couple of months ago. We also have a cup anemometer and a wind vane to measure wind speed and direction. We actually just swapped out one of the redundant cup anemometers to include an ultrasonic anemometer that also measures wind speed and direction. We measure solar radiation, air temperature and relative humidity, barometric pressure. And then on the oceanographic side, to support a lot of the analysis that Gabriel just talked about, we measure the water velocity profile. We have an instrument to measure salinity and water temperature. We measure the wave spectrum, and then an additional piece of instrumentation for more water temperature information. All right, so now I'm going to dive in and talk a little bit about some previous, recently completed, and near-term buoy activities. So after the buoys were procured and they underwent acceptance testing, they were transported to the East Coast and deployed off of New Jersey and Virginia between 2014 and 2017. The deployments were very successful. However, we learned that there were some limitations with the original LIDAR systems that were purchased with the buoys. Those were Vindicator 3 LIDAR systems. So we realized through these deployments that the laser power appeared to be low. And as a result, during periods of low carrier to noise ratio, the LIDAR systems tended to report wind speeds that were too low. And so that low speed bias was largely able to be removed with some post-processing, but at the cost of significantly reducing the data availability. And so for some of the range gates on the LIDARs that were collecting data, the data availability dropped to around 85%, which is below the Carbon Trust recommendation. So this is ultimately the reason why we upgraded our LIDAR systems. And so that upgrade was recently completed. Again, during the deployment, and as we were processing that data, we really, that really highlighted the need to upgrade our LIDARs to more powerful systems. And so in January of last year, of 2019, we issued a request for proposal. We put a contract in place with Ocean Tech Services to upgrade the LIDAR systems, to perform a validation, and also to do some additional upgrades to some data logging equipment. That was completed in the summer of last year, and then in the winter, spring of this year, the buoys were deployed off the coast of Martha's Vineyard, and the LIDARs were validated against a reference LIDAR on the Air-Sea Interaction Tower that's maintained by Woods Hole. And ultimately, we received a validation test report and independent certification from DNVGL. Just a little bit more about the validation. This was extremely important to do at the time we did it because, as I mentioned, the buoys are now staged in California. They're going to be deployed in partnership with BOEM to really inform offshore wind on the West Coast, to inform the development of their call areas and leasing process. And so we really needed to make sure that these LiDARs were validated to ensure that the data that they collect are bankable. And so, as I mentioned, the buoys were deployed, and the LiDARs were compared with reference LiDARs on the air-sea interaction tower between January and April of this year. The overall upgrade and validation was supervised by DNVGL, and these are copies or screenshots, I guess, of the independent performance verification reports for both LiDARs. I have some plots here that you can at least just see from a high level, that for both buoys, there are plots for both wind speed and direction. The correlation is excellent between the wind speed and direction on both buoys compared with the ACIT tower. Very, very high R squared with slopes that are very, very close to 1. Now moving forward to offshore wind in California, Raghu touched on this a little bit in terms of what the development potential is in California. And I know, again, that's why a lot of you are on this call today. And as I'm sure many of you are aware, in August of 2018, California, they really made history by passing SB 100, where California set a really big goal of powering the state with 100% clean, carbon-free electricity by 2045. And as this graphic shows, and as many of you are aware, there are lots of challenges that are facing offshore wind in California, including economic, regulatory, and environmental challenges. And a lot of those regulatory and environmental challenges have actually been talked about on some of these previous POET webinars. But in order to move the development on the West Coast forward, PNNL and DOE and BOEM are partnering to deploy these buoys off the coast of California to ensure that the necessary offshore data is collected to support wind resource characterization and model validation, and to be able to support their leasing process. And so, as I mentioned, our 2 buoys are staged in California right now. One is staged on the north coast to be deployed in the Humboldt call area, the other along the central coast in the Morro Bay area. And again, the purpose here really is to work with DOE and BOEM to partner to provide wind resource characterization and expanded model validation. The buoys are going to be deployed in the next 2 weeks or so. Both on the north coast and central coast. They'll be deployed for 12 months. All of that data will be made available on the DOE data archive and portal. And for the Humboldt call area on the north coast, we're going to be doing some additional environmental monitoring in terms of bird and bat monitoring using a thermal stereo vision technology called Thermal Tracker 3D that's been developed at PNNL. And Sherry Matzner, the PI of that work, presented on a previous POET webinar about her technology as well. In terms of what type of data analysis we're going to be doing with the data that we collect from California, again, Raghu and Mike and Gabriel talked about a lot of these things. We're going to be doing a turbulence evaluation based on the LiDAR and surface data. We're going to look at conventional wind profile errors. We're going to look at sea surface temperature variation over the deployment period. We're going to do a reanalysis. We're going to do an evaluation of reanalysis model errors, and also look at some case studies to understand large conditions of error. And as Mike said in his presentation, to date, they haven't had any floating LiDAR measurements yet. So the data that we collect during these deployments will ultimately be key for NREL's work. So they can use it for their validation to find the best model setup for offshore California. And so in summary, DOE is supporting several initiatives through their offshore wind resource characterization program, which is supporting offshore wind industry by identifying research needs for offshore wind resource evaluation, by investing in wind resource characterization and technology demonstration projects, and then ultimately supporting metocean data collection using validated methods, especially for the deployments upcoming off of California. And again, just a quick rundown of the timeline for the deployments off California. The buoys are commissioned right now. They're staged in California. They're going to be deployed in the next few weeks, and we're going to start collecting data. In March of 2021, we will have a scheduled maintenance visit where we'll go in and exchange some of the data cards so we can have access to that raw, high resolution data. The buoys will be recovered in September of 2021. And then throughout 2020 and 2021, we'll be doing some data analysis and reporting on the near real-time data that we receive from the deployments, and then also the raw data that we receive during the maintenance visit and at buoy recovery. And then after the California deployments, the buoys will be transported to the East Coast for an East Coast offshore wind resource science study. And so with that, thank you, and thanks to our whole kind of LIDAR buoy and LIDAR buoy science team at PNNL. Again, and thank you to DOE and BOEM for sponsoring and partnering on the upcoming deployments, and also to Ocean Tech Services and Axis Technologies, which are our two main contractors for this work. And with that, I'm going to pass my host privileges along to Frank Pendleton from the Bureau of Ocean Energy Management, if I can figure out how to do that. So just give me 1 second. There we go. Thank you, everybody.
All right, so I'm just checking in to make sure you can hear me and you're seeing my slideshow.
Well, we can hear you, but I don't see the slideshow yet.
All right, I can give that one more try here. There's the issue.
There we go.
How are we doing now?
Perfect, thank you.
All right, thank you. All right, well, thank you, everyone. I'm Frank Pendleton. I'm a GIS analyst for BOEM, the Bureau of Ocean Energy Management. And just to give you an idea of what we'll be covering today, I'll very briefly tell you about BOEM, who we are, and what we're up to in offshore wind. Talk a bit about why offshore wind in California, and particularly why floating offshore wind. Briefly, well, probably a little bit more than briefly, go over wind data for planning. How do we use that data as we're planning for offshore wind development? And then other planning concerns. There's a lot of other planning concerns aside from wind. Wind is crucial. Obviously, we're talking about wind energy, but there's a lot of other very important considerations. So in that, about BOEM and who we are, our mission is to manage the development of the U.S. Outer Continental Shelf for energy and mineral resources in an environmentally and economically responsible way. And we view Outer Continental Shelf different than geologists. This is the bureaucratic view, and it's basically the EEZ. And that's our jurisdiction from 3 out to 200 nautical miles. And it excludes national marine sanctuaries. So the map there kind of shows you the area we're talking about. And one of the, well, the most important tool we probably have for managing the EEZ is our leases. And here's the very brief explanation of our lease process. I won't go into any detail. One of our leasing specialists could talk about this for quite a while. But I just want to give you the very basics that right now in both in California and Oregon, we're here in stage 1, the first 2 years of planning and analysis. Oregon, we're pretty close to the beginning. California, we're getting closer to the end. And we're using wind data as part of that. You know, this is the 10,000 foot level. How windy is it in different places and getting a good idea of that. Then we'll go on to leasing. After that, it's site assessment, right? It's been leased. There's a developer looking to develop the site. They're going to need a lot more specific data about how does this place, how windy is this place and when and everything. And then finally, construction and operations. And yes, they're going to still need to know a lot more about the wind resource. So there's lots of uses for this throughout the leasing process. And the question of why offshore wind, right? Why not just on land? And as you've seen from the talks earlier, the ocean is windier, and that's a big deal. You can create a lot more energy from windier places, right? It makes sense. It's also windy at the right times. Now, this here, what we're seeing is the duck curve. And I specifically put the kind of my simple person's definition of it, the power that is needed from non-solar resources to meet California's electricity needs, right, at any given time. And in this case, we've got time in a couple of ways, right across the bottom here, the time of day. And, you know, over here on the y-axis is how much energy we need. But the different lines are corresponding with different years. And as California has done an excellent job and continues to promote solar, it's a great resource, but it does cause some issues. Each year, as more and more solar comes online, it's wonderful. At the middle of the day, when solar is at its max, it's lowering how much other electricity resources are needed. But as the sun starts to set, and everyone goes home and starts turning on their appliances and other things, there's a lot of electricity needed. And that gets us to this area where there's a huge ramp where we've really got to go from very little other resources to a lot of other resources. And that's a big deal if you're trying to manage the grid. And here's just one example of using some of the NREL data, right, where the end users of the data they create. And to get us to the idea of why wind fits into the grid so well. That as the sun's going down, the wind is at its peak. This is in Southern California, near where the call areas are, but not inland. And we'll look into this a little more later. And now specifically, why, instead of just offshore wind, why floating offshore wind? And it's a pretty simple answer. The West is very deep compared to the East. In the East, they're mostly looking at monopiles and jackets, but in the West, we've got to look at floating. And both of these maps are at the same scale. The light blue is the world of monopiles, the medium blue, jackets and such, and the deep blue is the world of floating. And you can see a lot of need for floating on the West Coast and also up here in Maine on the East Coast. And to give you a quick idea, I'm sure a lot of folks in this call are well aware of this, but some might not be. But in the shallows, less than 60, we're looking at the monopiles that are pounded right into the seafloor, or jackets, a similar type of setup, but for places that are a little deeper. Then as we get deeper than 60 meters, we enter the world of floating offshore wind. There's several different types of floating platforms that can be used. And we'll take a peek at a couple of them real briefly. This one on the far right is a spar, basically just a big tube that goes down in the water. And then a submerged, now I'm forgetting the rest of the name. It'll come to me, but a semi-submersible platform that can operate shallower than the spars. And what we've got right now, actually out operating in the field in Scotland in 2017, Highwind put in 5 spars. They have 5 turbines, each is 6 megawatts for a total of 30 megawatts. And it's operating at 130 meter depth. So that was kind of the first real grid connected for the purpose of producing electricity wind farm. Just recently, Windfloat Atlantic off of Portugal put out 3 of their semi-submersibles. And it's 3 turbines, and they're using even bigger turbines, 8.4 megawatt turbines for a total of about 25 megawatts on just 3 turbines. And they're at about 100 meter depth. So it's starting to take off, the floating. It's getting beyond the concept idea. And if you want to know more about a floating offshore wind, the talk that was done by Walt Musial at NREL, it's an excellent talk. If you just Google floating offshore wind NREL, you'll get to this. It's just about an hour long. It's definitely worth your time. And now to get where BOEM gets our wind speed data. You know, as you heard earlier, you can see we work closely with NREL and others to get the data. Ultimately, the data we use comes from NREL. And when I was talking with some of their scientists in the past about, well, where does the data actually come from when you send me these points that are wind data? And they started explaining it to me, but as you can see from the math equations and everything they were talking about, it's in-depth science. And ultimately, for my simple brain, they sent me this picture, which kind of gets it to me. It comes from many sources, and it's all brought in together. And you've heard all you need to hear about that earlier. So it's a complicated process, bringing a lot of different data sources together. And the data that NREL makes for us, it's ultimately available on the Wind Prospector. You heard Mike talk about that earlier. And here's an example of it, and it starts to get to how we're using it. It's ultimately points, and here you can see the points. This is just zoomed in off of the Humboldt Eureka Arcata area. And you can see there's points roughly about every 2 kilometers. That gives you wind speed. So you know the where is it windy. And over here you can see that they do make it available each month, which is very useful to us. But more than just each month, if you dig into these points and look behind the data, you get hourly wind speeds. So here's January at midnight, January at 1, January at 2. Obviously, it keeps going on. So you can really start to look more in depth at when is it windy, where. And that allows us to develop these graphs that really give us a good idea of how is this, if we develop a wind farm here, how is it going to fit into the whole electrical system. So as Alicia gave you a lot of details on the LiDAR buoys that we are cooperating with DOE and PNNL, but the LiDAR buoys out there, they're going at 2 of our call areas. We'll talk more about these call areas as we go on. Alicia explained everything here, and just part of the reason we're so interested is the proof of concept, putting them out at places where it's so deep so we know it can work. To test other devices. Alicia mentioned about the bird devices and the bird and bat detectors. To validate data sets, as you heard earlier, that there's more real in-depth data needed to validate these data sets. And also data for other research projects. Other research institutions we're working with are very interested in having this detailed data to do further analysis on economics and other items of interest. So we're really looking forward to this. And now, so what we get to the idea, we know so much about wind, there's good wind dating, right? Planning is easy. Let's just put the turbines in the windy spots, right? Well, not so fast, right? There are a lot of limitations and considerations. So I'm gonna walk you through a few of those and get you to the idea of why our first set of call areas are where they are. And as we talked earlier, the area of BOEM jurisdiction from 3 out to 200 nautical miles. So that gives us quite a large area to work from, to look at putting in floating offshore wind turbines. But if we take that and limit it by a reasonable depth, about 1,300 meters, that's still quite deep. We're down to 16% of what we started, or 34,000 square miles. Now, if we use the wind data, obviously we're looking at putting out turbines. Wind data is key. That cuts out quite a bit more, and we're down to 9% of the EEZ, the Outer Continental Shelf there. Now, if we take the areas that we don't have any jurisdiction, the national marine sanctuaries, California's done a great job of developing their national marine sanctuaries. BOEM doesn't have jurisdiction there. So now we're down to just 6% of the EEZ, where we can really start looking in more depth for wind. There's some other limits that I'm going to stop with the cutting things off at the percent. You get the idea. But some other limits that are very important to making this economic possible. What other environmental factors come into this? Very strong one is how close are you to a grid connection? And as you can see here, the grid connections, the pinker and the smaller the circle, the smaller the grid connection. You've got the transmission lines, the lighter and the skinnier, the smaller the transmission lines. Big blue ones are what we need to move things along. So you can see we've got a few things up here in Humboldt, not connected to anything really big, but they are for Humboldt, not a ton of people living up there. It's possible to do a local project and then for the longer term, think more about how we're going to get this wind somewhere else. Down here in the Morro Bay area, there's the Morro Bay power plant that went offline a few years back. So all the wires are still there. The actual substation is there, connection to the grid. So that's a consideration. Just south of it, there's the Diablo Canyon, which is going offline 2024, 2025, sometime around there. And it has very big plug and very big wires coming out. So these are strong considerations. So in this case, we're just zooming in just to take a closer peek of where our call areas are. So these are the areas that we've reached out to get more information about and are looking to lease in the future, possibly. Here's the Humboldt call area. Just the two call areas that ended up down in the Morro Bay area. The Morro Bay call, either quite close there to the large plugs that lead to larger wires. Some other considerations: submarine cables. So you can't be putting huge anchors on cables. Distance from shore. This is nothing hard and fast, how far you can get from shore. But in general, as you go further, the trend is better for things like viewshed, fisheries, marine mammals, and birds, right? It's when they're further away, you don't see them as much. A lot of fishing near shore. Sure, there's fishing offshore, and it's definitely still going to be something we have to look at. Marine mammals still have to look at. But the trend tends to get better as you're further offshore. But as it trends closer, it's better for the availability, more offshore wind areas, less miles of cable. It's very expensive cable, and maintenance becomes a lot more reasonable, a lot cheaper. Other considerations: the Department of Defense is they've evaluated the coast for how important is it to defense purposes and rated it red, yellow, or green. As you can see, a good part of the Southern California, well, all of Southern California and most Central, has been rated red. So there's discussions going on, obviously well above my head, about how can we make this work. Another consideration is slope. How steep is it? You can't put these in places where it's really steep. And this just gives you an idea. As we go a little deeper than the 1,300 meters, not only are we getting deeper, but we're dropping off a very steep slope. So you can't use this and then you get very deep. So it's an important consideration. And one last kind of non-physical thing we'll talk about is vessel traffic. When we first created these, 2011 was the best vessel traffic data, the newest available. But some laws have changed. So where vessels go has changed as well. So you can see they've moved closer to shore. So in this case, we're in contact with the Coast Guard and having discussions about how is this going to play in. And lastly, I'll tell you about, this is a lot of things on this last slide, but a lot of the biology and other factors that are not like just a straight up can't put it here type of factor. And we've been having a science exchange, a BOEM science exchange that's been going on for several months. And there's been a lot of different talks regarding these different factors. And you can get to this site and you can see the slides from all the older talks. But coming up soon in September 9th at 10 a.m. Pacific time, there'll be a talk regarding benthic habitats and geohazards on the West Coast. So we invite you to come check out that one, but you can also see all the talks from past talks here. And so to kind of summarize, the bottom line is good wind data. It's vital. You cannot put turbines out where there's not good wind data. It's very important to know where it's windy. It's important to know when it's windy. And it's important to know how windy it is. Right? And wind data is constantly improving. So at BOEM, we're happy to be working with these other organizations that are on the forefront of improving this wind data. It's going to make for better planning as we go forward. And just lastly, there are many considerations when planning for offshore wind, aside from the wind. And that's it for me. And I will just forward it to the final slide here and let you take over, Matt.
Awesome. Thank you very much, Frank, and to all our presenters. We have about 10 minutes left here to go through some questions, and it looks like we've been able to answer some of the questions as we've gone, but I'm still documenting them here, and go ahead and ask our panelists what I'm pretty sure you guys didn't cover. So I'm going to start with Raghu, and I'm just going to read the question as it was submitted. So how important was the HF radar to the study referenced?
Not sure which study you guys were talking about in particular. So I'm
okay.
But yeah, that would maybe.
That's all right. We can go ahead and skip that. If whoever asked that question wanted to be more specific, we could do that. And I'll also preface this by saying, if anyone has any further questions, please go ahead and send us an email at info@pacificoceanenergy.org, and we're happy to connect you to the panelists for additional follow-up. So I'll move on. Mike, I think this next question was for you, but obviously any of the panelists are welcome to answer these. In terms of differences between the new and old data, do you see shifts in general temporal patterns or magnitude, or both? Can the old data still be used for regional, not site-specific analysis if you don't need model sensitivity, or do you suggest using the new data for all applications?
Yeah, thanks, Matt, for the question. I'll address the last one first. I think we would like to see the new data being used, just given, it's more modern, what we believe more accurate data set, and just given the differences we're seeing on a mean annual basis, and the fact that it's a full 20-year data set and more appropriate for long-term analyses, we certainly would recommend the use of it. I think using the wind toolkit still is fine too in combination, because I've talked a lot about model sensitivity and the need to understand that in your analyses. So running both models may not be a bad idea as well. In terms of the temporal changes, we are seeing some. I know Frank talked about the diurnal cycle from the wind toolkit and matching California loads in the south. All that's still true with the new data set. It's just the magnitude or the amplitude of that diurnal cycle is slightly different given the different turbulence schemes and how they account for different stability regimes. So the general story is not going to change, but it's more just the magnitude of that cycle. Did I miss any part of that question?
Not that I'm aware of, but we'll go ahead. I'm going to ask a softball question for everybody here. What have been the perspectives of European offshore wind energy companies on information needs for wind resource assessment? If anyone has any experience with that, feel free to jump in.
Sure. I can that. I think the European experience has they've had a lot of experience, of course, kind of putting up a lot of the offshore wind turbines. And one of the experiences, I guess, is trying to improve our understanding of the spatial variability of the winds. Understanding the spatial variability of the winds relative to the coast is something that is deemed to be extremely important. And they also have noticed or observed that measurements such as precipitation can really help improve or mitigate the blade erosion effects, and that's something which has been lacking currently in our ITS. So some of the experiences which the European partners or industry folks have attained to, I think we're kind of focusing on that and trying to build upon that.
Great, thank you very much for that answer. Gonna move on. I think this next one might have been for Mike as well. Mike, can you comment on the vertical resolution you were using in the new method to resolve stable conditions near the sea surface? And does it include a convective scheme?
Yeah, the work model definitely has a convective scheme that works in these unstable conditions. In terms of our model vertical resolution, we've more or less doubled it from the wind toolkit. There's about 9 or 10 levels below 200 meters, depending on atmospheric conditions. Those heights tend to, they're based on fractions of surface pressures. They're not always at the same height. But regardless, it's pretty high near the surface, starting around 11 meters, 35 meters, 51 meters on average. So we've really upped the resolution and are better resolving the lower 200 meters than we've ever been before.
Great, thank you. There's a question in the Q&A that if someone has a quick ability to post that link, it would be helpful. If you could please post a link to the NREL 20-year offshore wind data set for California. Otherwise, if someone wants to put that in a slide, these presentations will be made available later so people can find the answer to that. One last question, and this one would be for anybody, any of the panelists. What sort of coordination, planning, and approvals were needed to deploy the buoys off California?
So this is Alicia. I can take a stab at that, and I can also let Frank chime in as well, because as it turns out, Frank and I work very closely on the deployment of the buoys. But for the deployments off California, there was just a lot of coordination between DOE, PNNL, and BOEM. And the first part of all of that is siting. And so in order to site where the buoys were going to be deployed in the Morro Bay and Humboldt Call area, we had to look at offshore wind speed information, oceanographic information such as wave heights and currents, the water depth, the bottom type. We also looked at vessel traffic in the area, competing ocean uses, sensitive species habitat. So lots and lots of different things in terms of siting where these buoys were going to go. PNNL, while we assist in siting and permitting for the deployments, we actually don't physically deploy the buoys ourselves. We work with a deployment contractor for them to deploy the buoys and to do a lot of the logistical planning. And for the California deployments, that contractor is Axis Technologies. We also coordinate with contractors on designing the mooring systems for both buoys. This environment off the West Coast is very, very different from the deployment environments off the East Coast. We're obviously in a very different wave environment, as Gabriel talked about. And the water depth here is much, much deeper. Starting for the Humboldt Call area at about 650 meters, and then for the Morro Bay Call area, it's about 1,000 meters. So just a lot more complexity that goes into the mooring design there. And then I also mentioned that PNNL is involved in the permitting aspects. So there's just a lot of coordination between PNNL and BOEM and other agencies such as State Historic Preservation Office, NOAA's National Marine Fisheries Service, the U.S. Fish and Wildlife, the Army Corps, and also the Coast Guard. So we have to make sure that we keep them all aware of our plans, and we're actively talking with the Coast Guard now, being that the deployments are rapidly approaching.
Is there any potential for additional buoy deployments? A quick question just came in there from Chris Potter.
Off California? Or just along off California. I mean, I don't know. I mean, there's been a lot of interest in deploying additional buoys off California and Oregon, but there haven't been any formal discussions yet. The buoys will be deployed off the East Coast, probably late in 2021 or in 2022. So they do have a deployment planned, but there haven't been any formal discussions yet about additional deployments off the West Coast.
Great, thanks for that answer. So we're at time here. I think we've answered the majority of the questions that came in. So I think we'll go ahead and wrap this up for today. I do want to thank all of our panelists. This was a really fantastic webinar. We really appreciate all your expertise and time that you put into this. We thank you all for attending. Feel free to, like I said, send any questions to our info@pacificoceanenergy.org email address. We're happy to direct those to the panelists and get your questions answered. And we encourage you to stay tuned and look forward to Poet's upcoming webinar. Hopefully later in September, we'll provide more information about that as it becomes available. Everyone stay well, be safe, and we look forward to working with you again in the future. Take care.
Thank you.